You have a little tiny fuel pellet, 1 millimeter in size, and it's filled with fusion fuel, and it gives off a burst of energy, enough energy to power the average UK home for 2 years.
This all started with the shrimp, not the kind you eat, but one so powerful it creates plasma with a snap of its claw. Strange? Definitely. But somehow, that bizarre little creature inspired one of the most radical approaches to fusion energy we've ever seen. In a world racing to solve the energy crisis, a UK company called First Light Fusion is building machines that don't just simulate stars, they slam matter together at speeds faster than bullets. It sounds chaotic. It sounds reckless. But what if that's exactly what we need? What if smashing things is the smartest idea of all? The race for fusion. For decades, nuclear fusion has been the dream everyone's been chasing. Clean energy, limitless fuel, and no meltdown risk. But so far, it's remained just that. A dream. That is, until now. A silent race has begun. Not between nations this time, but between startups, backed by billionaires and physicists with wild ideas. In 2022 alone, private investment in fusion shot up to nearly $5 billion. Compare that to public funding, which barely touched $120 million. Still, when stacked against $500 billion in global renewable energy investments that same year, fusion is barely a ripple. Yet, the urgency is real. With the climate clock ticking, fusion has moved from labs to boardrooms. The UK is taking the challenge seriously. At the heart of its strategy sits the Culham Science Centre, home to the UK Atomic Energy Authority. It's where legacy machines like JET and MAST-U live, classic tokamaks trying to recreate the sun's power. But Culham isn't just a government lab anymore. It has become a launchpad for private fusion companies like First Light Fusion. The idea? Let these unconventional thinkers use the tools, data, and support of the state, and maybe, just maybe, build something no one else dares to. The idea that changed everything. It didn't start in a reactor or a government lab. It started in the ocean with a shrimp. A pistol shrimp, to be exact. When it snaps its claw, it sends a shock wave through the water so fast and violently that it forms a bubble. That bubble collapses in on itself, creating a tiny pocket of plasma hotter than the surface of the sun. That single natural event sparked an idea in the mind of physicist Nick Hawker. Could the same principle be scaled up? Could impact-driven collapse trigger fusion? That shrimp snap became the seed for years of research, trial, and simulation. Nick and his team tried to capture the raw physics of that moment, compressing a gas, creating a shock wave, generating extreme pressure, and feeding it into computers. It's completely different now, Nick explains. But that shrimp moment was the start. What emerged was a new class of inertial confinement fusion, one that didn't rely on lasers or giant magnets. Instead, it used brute force, speed, and precision, like distilling nature's violence into a repeatable rhythm. The idea was bold, but the science held promise. And from that rhythm, First Light's fusion method was born, not from theory, but from nature's most violent elegance. What is projectile fusion? At its core, First Light Fusion's method is stunningly simple. Take a tiny disk of fuel, fire something into it at extreme speed, and let the resulting chaos do the rest. This isn't theoretical anymore. They've done it. It's called projectile fusion, and it builds on an old concept known as inertial confinement fusion. But instead of lasers or magnetic fields, they use a physical projectile launched into a small fuel capsule. Picture it like an engine. The projectile is the spark plug. The fuel, usually deuterium and tritium, sits in the chamber. When the projectile slams into the target, it creates a powerful shockwave. That shockwave collapses the fuel inward, increasing the pressure and temperature so dramatically that the atoms are forced to fuse. And when that happens, energy is released. Their fuel target is only a few millimeters across, but the shape and structure are carefully designed to funnel the shockwave inward, focusing it just enough to ignite the reaction. Every curve, every layer of the target plays a role. The projectile itself must remain solid until the very last moment. And all of this happens in an instant. No moving pistons, no spinning turbines. Just one brutal, well-aimed hit, like striking the heart of a star with a bullet. And it works. Inside the machines, Machine 1 and 2. To make this work, First Light Fusion had to build machines capable of weaponizing precision. Their first machine looks almost like a giant cannon, and in a way, it is. Machine 1 uses a two-stage light gas gun. The first stage uses gunpowder to fire a piston. That piston compresses hydrogen gas, which then launches the second projectile at nearly 7 kilometers per second. Not fast enough for fusion, but fast enough to test the physics of impact, energy transfer, and target response. Then came Machine 2, the move from combustion to electromagnetism. This machine uses pulse power to accelerate a projectile without any explosives. Instead, powerful electromagnetic pulses do the heavy lifting. It's quieter, cleaner, and more scalable, allowing for more precise control of velocity and timing. Machine 2 also allowed them to study the projectile mid-flight. Using an X-ray pulse from a second power system, they captured detailed images of the projectile in motion. Was it intact? Was it deforming? Was it spinning? Every detail mattered because at 60 km/s, there's no room for error. What they're building is less like a gun and more like a scientific slingshot designed for atomic precision. Machine 3, the giant pulse. Machine 3 is where things start to feel surreal. It doesn't look like a reactor. It looks like something out of science fiction. A massive circular structure wrapped in cables, switches, and silence. At its heart is a vacuum chamber. Around it, 192 capacitors store a terrifying amount of energy. Each one is charged to plus 100 kilovolts. But what's wild isn't the number, it's how that power moves. No cables are running to the core. Instead, the walkways, thick aluminum plates, are the wires. When the capacitors fire, current rushes through these plates and into the chamber. Inside, two massive currents meet and generate a magnetic field of 500 Tesla. That's enough to rip a postage stamp-sized piece of metal clean off a larger assembly and hurl it forward at 15 kilometers per second. That tiny projectile, just a sliver, is the bullet aimed at fusion. It's ripped free by magnetic violence and slammed into the target. The chamber shakes. The air smells different, and somehow, in that brutal moment, energy is born. It's industrial alchemy, not magic. But it feels like both when you see it in motion. What comes next? Machine 4. Machine 3 is impressive, but it's just the warm-up. The real show is Machine 4, currently under construction at the Cullum Science Center. If Machine 3 is a cannon, then Machine 4 is a planetary weapon. It will house 8,000 capacitors, more than 40 times what Machine 3 holds, and stretch across 75 meters in diameter. This beast will launch projectiles at a mind-bending 60 kilometers per second. Yet, despite its scale, Machine 4 won't cost billions. It's surprisingly cheap. First Light estimates around $2 per joule of energy, compared to the $2,000 per joule price tag of some laser-based systems. That's not just efficient, it's revolutionary. But this isn't about showing off. Machine 4 is their amplification demonstrator. Its job is to prove, without doubt, that fusion via projectiles can scale. It's not the final power plant, but it's the moment the idea goes from theory to industrial reality. Solving the tritium problem. Even if the fusion works, there's a catch. Fuel, more specifically, tritium. It's rare, radioactive, and expensive. There's barely enough on Earth to run even one fusion plant for more than a few weeks. Every fusion company has to face this wall eventually. But First Light claims they've already built a ladder over it. Their approach allows them to use almost the entire 310 around the reactor target to breed tritium. In comparison, tokamaks are bulky and filled with magnets or optics, which take up critical space. This means First Light's setup could generate more tritium than it consumes, closing the fuel loop completely. That's a game changer. Even more, they can overproduce tritium during early plant operations, stockpiling it for the next generation of reactors. In a field where tritium often spells doom for scalability, First Light's method may be the first true path to fuel independence and, eventually, commercial fusion. Philosophy of simplicity. What struck me most wasn't the machines. It was the mindset behind them. Nick Hawker explained it best. "Our design is incredibly intricate," he said, "so complex that even we can't always trace the exact chain of cause and effect. The simulations show everything working. The energy focuses, the pressure spikes, and fusion happens. But try to isolate the exact moment it all aligns? You can't. And yet, the method is brutally simple. At the end of the day, all their careful design, the simulations, the shaping, the capacitors, lead to one thing: hitting a fuel pellet in the face with a metal slug. It's finesse on the inside," Nick laughed, "and blunt force on the outside. It's that contradiction, precision wrapped in chaos, that makes First Light fusion different. Because maybe fusion doesn't have to be gentle. Maybe it has to be bold." This all began with the snap of a shrimp claw, a violent burst of nature that somehow pointed us toward the future of clean energy. First Light. Fusion isn't promising miracles. They're building machines, running tests, and preparing for a decade-long journey. But they've already shown what's possible when you stop trying to mimic stars and start thinking like nature. Machine 4 is coming. And if it works, it won't just be a win for them. It could shift the fusion conversation entirely. Until then, the question remains: what if smashing things is exactly how we build the future?